This set of notes allows us to continue looking at ways we can assess the fit of a model. In the past, we were looking at, for one particular observation, we would calculate a standardized Pearson residual, and that would give us some information about how well the model fits that one particular observation. But instead, you may be interested in looking at ways to come up with an overall general measure for the entire data set, how well the model fits the data. And that's the purpose of goodness of fit statistics. Now, two commonly used goodness of fit statistics are a Pearson statistic and a residual deviance. We've obviously already looked at a residual deviance before, and it helps us compare our model of interest to a saturated model. A Pearson statistic does the same thing, where all we do is we square those Pearson residuals, and then across the entire set of observations, and then we add them all up to come up with one overall goodness of fit statistic. We'll call it x squared. So some questions then is, why do you think that these statistics would be useful to examine? Well, simply, it gives one overall measure of how well the model fits the data, rather than looking at individual standardized Pearson residuals for every single observation in the data set. So it's one overall measure. The statistics are then used for a goodness of fit test, where simply the null hypothesis represents, in words, the model fits the data well. The alternative hypothesis, in words, the model does not fit the data well. Compare this to what we were seeing before when we were looking at a residual deviance statistic and actually writing out hypotheses formally. What types of values for x squared and d would lead to a rejection of the null hypothesis? Well, this goes back to, well, what does a Pearson residual represent? Well, it's a measure of how well that observation is fit by the model. Values outside plus or minus 2 indicate that particular observation perhaps does not fit well. So when I square that, now we're looking at values values greater than 4 for that Pearson residual. And if I were to sum those all up across the entire data set, what we can see is that, hey, if we have an x squared large, then that gives us indication that perhaps the model is not fit well. Perhaps the data is not fit well by the model. Now, these statistics have an approximate chi-square distributions with them, with m minus p tilde degrees of freedom. Not for sure why we chose p tilde here. All this represents as p plus 1, essentially the number of regression parameters. Anyway, we chose to use p tilde. And so what that means is that we can use, let's say, a 1 minus alpha quantile from this chi-square distribution to judge whether or not the model is fit well or not. To judge whether or not the data is fit well or not by the model. Now, unfortunately, this chi-square distribution approximation often does not work well. And the reason being is because basically it assumes that the number of unique explanatory variable combinations, in terms of a logistic regression model, when we were looking at EVPs, that remains fixed as the sample size increases. If that doesn't occur, then this chi-square distribution approximation may not work well. So if you end up having, let's say, a continuous explanatory variable in your data set, then this particular statistic is one that you would not want to use with a chi-square distribution approximation. So alternatively, an informal measure of goodness of fit is as follows. Take your residual deviance divided by its corresponding degrees of freedom, which would be number of observations minus the number of parameters being estimated. Now, if this model is reasonable for the data, then this numerical value should not be too far from 1. So you might be saying, well, how far is too far? Here are some general guidelines. So maybe you have a potential problem with your model if this deviance divided by degrees of freedom statistic is greater than 1 plus 2 times the square root of 2 divided by n minus p. Poor fit if now instead of that 2 we have a 3 there instead. Well, where does this come from? Well, basically it still sort of uses this chi-square distribution approximation that we were talking about before. So you're not responsible, if you're a student in my class, you're not responsible for this, this here because it relies on some mathematical statistics in terms of having a mathematical statistics course background. And the variance of this statistic is equal to 1 over n minus p quantity squared times the variance of d. And if d was well approximated by this chi-square distribution, then we would know that the expected value of d would be approximately n minus p tilde. The variance of d would be approximately 2 times n minus p. Where does this come from? If you had a mathematical statistics course, you know that a chi-square random variable has a mean that's equal to the degrees of freedom, and a variance is equal to 2 times the degrees of freedom. So using that, and essentially that rule of thumb that you would learn about in your first stat course about the number of standard deviations, all, let's say, data lies from its mean, like 2 to 3 standard deviations. Using that then, essentially what we're doing is we're taking the mean plus 2 times the standard deviation of our statistic here. Now you might be wondering, well, wait a second, you were just telling me that this chi-square distribution approximation may not work. That is true, but it will tend to, approximations like this will tend to work much better in with respect to its moments rather than the extreme tail portions of a distribution. So that's why we use this measure. It's definitely not perfect, but it is better than using the chi-square distribution approximation fully. Now, if you're interested, there are other goodness of fit measures as well. None of them are perfect. You can take a look at my book if you're interested in seeing them further. Okay, we'll look at an example shortly that applies some of these ideas to some data. Next, another way to assess the fit of a model is to examine the influence a particular observation has on the end model that you get, and estimated model that you get. What I mean by that, I kind of just have described in the past, and that is, let's say you estimate your model, and then let's say that you remove one observation from the data set and re-estimate the model. If the model's changed a lot, then that observation that you removed is influential. And you would want to figure out, well, why is it influential? Is it influential in a bad way too? Does it change your inferences that you would be making? And so it's helpful then to come up with a statistic that's, or a variety of statistics that's based upon that idea of let's remove one observation, let's say temporarily, refit the model and see what happens. Does the model change? And so that's the kinds of statistics that we're going to be looking at here. Now, as you might imagine, if you have a large data set, removing one observation at a time and re-estimating the model could be a time-consuming process. So because of that, instead of actually performing that idea, approximations have been developed by statisticians to measure what the effect would be from removing an observation from a data set. Now, one of these measures has been developed, is called Cook's distance. It was developed by Dennis Cook. This is a commonly used statistic in normal linear regression. It just simply has been modified now for the kinds of models that we're looking at. So for the nth observation, then the Cook's distance value is this quantity right here. This quantity ends up always being greater than 0. And it basically measures like an overall, how do the regression parameter estimates change for your model. Now, what values do you look at here to make a judgment then about, hey, is there a problem? General recommendations given by Cook and others is to look at greater than 1, or maybe greater than 4 divided by m. And notice how we have may here. So this is like an indication of, hey, if this happens, hey, you might want to take a closer look at it before you actually conclude it is influential, and before you actually conclude that it's influential in a bad way. Now, also some people will say, well, just look at all the Cook's distance values, and if you see some that are quite different from the others, then that would be a warning sign too. Now we could also look at the change in the Pearson goodness of fit statistic value, so that x squared. If I remove an observation from the data set, re-estimate the model, recalculate the Pearson statistic, does that change a lot? If it does, then that would say, hey, something's happening here. That observation that's removal caused something different to happen. The statistic is often referred to as delta x squared, where delta means change. So essentially, what happens to the x squared statistic? How does it change if the observation is removed? And in the end, it ends up being simply what we've seen before. The standardized Pearson residual, now just squared. That's it. So it's obviously quite easy to work with here. Now one could use a chi-square 1 approximation with this statistic to judge whether or not something is, let's say, unusually influential or not, meaning values that are maybe, let's say, greater than the 1 minus alpha quantile from that chi-square distribution indicate that. However, the same problems that we've seen before occur here in terms of a distributional approximation may not work out well. Let me also back up here a second too. So you might be wondering why we're using a chi-square 1. If you've had a mathematical statistics course, you know that a standard normal random variable, when it's squared, is equivalent to a chi-square 1. That's why. If you haven't had a mathematical statistics course, that's okay. Just accept this as this is true. So very roughly then, what we've done before with a standard normal for just the standardized Pearson residual, we looked at plus or minus 2 or plus or minus 3. Values outside that are some guidelines to look at further of, yes, that might be an outlier or an observation that's not fit well. Here in this particular case, if I take plus or minus 2 squared, I get 4. Plus or minus 3 squared, I get 9. And we can use that as a threshold. In a very similar manner, you can look at the change in the residual deviance as well. There's what the statistics look like. Use the same thresholds that we have here. And lastly, one could go to the hat matrix, diagonal values. We briefly have seen those described before. Let me give you a little bit more background on what you would learn about in a normal linear regression class to help understand what these measures represent. Okay, so imagine we have a scatter plot. We are just doing regular old normal linear regression. Here's my scatter plot of my data, and we could estimate a regression model that goes through what should be the middle of those points there. And what a hat matrix diagonal value ends up measuring is something called leverage. And you can think of leverage as this way. If I had an observation right here, what's going to happen is that point is going to have leverage in terms of it's going to pull down that red line towards it. And the hat matrix diagonal value for that particular case will be large because of this influence that this particular observation has. And so one could look at then the hat matrix diagonal values as well with respect to our models here. However, unfortunately, these measures don't work out as well with generalized linear models as they do with just the normal linear regression case of generalized linear models. And so because of that, I rarely will ever look at that. But what you will see in some plots coming up, I do include it on my my plot because some people do like to look at them. Okay. And note that there are certain thresholds with this too. These thresholds, once again, should be use more as a guide of, okay, I should look into this observation a little bit further to see if there is truly a problem. Now, how can we do the calculation here in R? Here are the corresponding functions for the hat matrix diagonal values, Cook's distance. We've already seen the standardized Pearson residuals before. All we would need to do is just simply square the value that we get from the R standard function. To do the change in D, the change in the deviance statistic, we can use the R standard function as well. Just change the type argument to deviance. Now, my book talks about a particular function that's in this file called GLM Diagnostics that will calculate this stuff in a nice organized manner. You're welcome to take a look at it. I'm going to focus, though, here on one other function that's introduced a little bit later in Chapter 5 called examine.logistic.reg, which basically does what this does here, but specifically for logistic regression models. Okay, before we get to that function, let me talk about one particular plot that's actually produced by this function. And it looks like this. So we have the delta x squared. Of course, remember, that's the standardized Pearson residual squared. It's plotted against pi hat. Now, in the past, we've actually seen a plot that looked like this. We had pi hat. We've had the standardized Pearson residual there. Let me draw a line here at 3. Let me draw a line here at -3. And we've seen how we might have a scattering of points that looks like this. And then towards the boundaries there for pi, in terms of between 0 and 1, we have some values that extend upon that, or above it, or below it for -3. And we talked about how in certain situations, those points should not necessarily be of concern for a logistic regression model in terms of assessing its fit. Now, if I were to square these corresponding standardized Pearson residuals, then I get this corresponding plot here. We have lines drawn at 4 and 9 as thresholds. And notice how we have this kind of an interesting pattern that occurs like this. And once again, in certain situations, such as, let's say, if I have a small number of trials for particular observations, we shouldn't be worried about seeing something like this. This is essentially to be expected. You can imagine a particular case if, let's say, n sub m is equal to 1, and if I have a low pi hat, but w sub m ends up being 1, well, what's going to happen is I'm going to have some value up there. I know that that particular delta chi-squared value is not necessarily going to be well approximated by a chi-squared distribution. Okay. Now, one last thing. Now, if you are concerned about how well a particular observation is doing in terms of if it's influential, one thing that you can do is actually yourself remove it from the data set temporarily, re-estimate the model, check, for example, your beta hats, maybe check some of your other measures regarding your model's fit, and actually look to see, is there a significant change there? If your inferences aren't really affected, if your predictions aren't really affected, then in the end, it might not be necessarily a big deal to have this particular influential observation in your data set, and your modeling will be fine. Now, another situation is that or what can happen is that a particular observation is influential for a reason, a good reason. And we'll see that here shortly. And that won't be something necessarily potentially of concern. Okay, so we're going to go back to the place-kicking data set. My examinlogistic.reg program is in that particular file there. And similar to what we've done before, read in the place-kicking data set, change it to EVP form, and then to get this examine.logistic.reg function ready to go, one way is I can open up then the corresponding file in my in my editor. This is what the file looks like. You're welcome to take a look at the corresponding code. If you're in my class, I recommend doing that, but you're not necessarily responsible for the details within it. It can help to understand the details, but I won't ask a direct question about the details within it. And to get this function then ready to go in R, what I can do is just simply highlight the code, run it, and now it's ready to go. Alternatively, what one could do is that if you know the location on your computer where you have actually saved that corresponding program, you can use the function called source that will automatically read in the program, run it into R, and now you're ready to go. Okay, so let's go ahead and try this particular function. So examine.logistic.reg. The first argument here is mod.fit.obj for object, your model fit object. So I've saved my results from GLM into mod.fit_bin. And then I'm also going to put an argument here called identify points equal true. What this will allow me to do is, you'll see in a few seconds here, it allows me to interactively click on certain points in my plot so that I can identify what those points are in terms of like the observation number. I'm going to save the results into save.info1. This is actually going to give me the numerical values for the various measures that we've looked at, including like the standardized Pearson residuals, the Cook's distance, and stuff like that. So let me go ahead and run it, and look what's going to happen here. A plot pops up. I have standardized residuals on the y-axis. I have the estimated probabilities on the x-axis. And notice my cursor here. It's a plus sign now. The reason being is because R is expecting me to add something to the plot in terms of, if I click on one of these points, look what happens. The actual observation number corresponding to that point is given now on the plot. The reason why I've incorporated that into my function is so that you can easily identify particular observations by their number, and that we can go back and investigate them more later. For some reason, there we go. Sorry, I was clicking on the wrong point. Now, once you're done identifying those points, and notice which ones I did, those that are essentially outside plus or minus 2, I can right-click to say stop. And now I have a new plot that pops up. First, though, on the previous plot, notice what's added. Basically, a low-S regression model to help you see trends. Remember, be very careful about interpreting this kind of a plot towards the boundary lines relative to the x-axis. The next plot is the Cook's distance plotted against the HAP matrix diagonal value. Now, if you notice here, we have some dashed lines here corresponding to the boundary lines that, or the recommendations that were given in the notes in terms of finding values that or observations that may be of concern. And if I come over here, we can see one that is way different from the rest. So if I click on that, it happens to be observation number 3 again. I'm done clicking on these points, so I right click and I say stop. Then I come down here, I have the delta x squares plotted versus the estimated probabilities. And the actual plotting point itself is now proportional to the number of trials. In other words, n sub m. The reason why I did that is because, remember, we are concerned if these chi-square approximation will actually work. I need a larger number of trials so that the continuous distribution approximation works. And so we can see here with a big circle here, that means I have a lot of trials. A very small circle means I have very few. More on that coming up here. So I want to identify some of these points that are kind of outlined here and compare this to the plot that is actually above it. Remember, all we're doing is we're squaring this standardized Pearson residuals. So I right click now, do stop, and we get a similar plot for now the delta x squared versus the estimated probability, but now the plotting point is proportional to the size of Cook's distance. The larger the plotting point, the larger the Cook's distance. And we can see that the big circle there corresponds to number 3, and we can see where that was on that particular plot too. So if I click on stop again, that's all the plots that are done. Down below, I have that deviance divided by degrees of freedom statistic. It ends up being 1.09. And then I also have that 2 standard deviation, 3 standard deviation thresholds. Notice 1.09 is less than those thresholds. So in terms of overall goodness of fit, this model looks to be okay. So let me come back over here to my notes. So now you should be thinking about, well, what do you think of the model here? Overall, things are okay, except for we have a few observations that we want to investigate further. We will do that very shortly. One thing I want to point out is that we can see how small some of those plotting points are relative to that big circle for number 3. Number 3 corresponds to the 20-yard place kicks. And remember, we had a lot of point after touchdowns there. And this particular observation represents about half of the total number of place kicks that were actually attempted relative to that data set. And so that's why that big circle is so big. But since it's so big, it kind of distorts from the sizing of all the other points. So what I've done is I've actually built in additional arguments, scale.n and scale.cookd, so that for the bottom left-hand side plot, the bottom right-hand side plot, you can change how the scaling of the points, the relative sizes, by some kind of transformation. So if I use a square root transformation, so instead of plotting, let's say, n sub m as the size of the plotting point, instead I could do the square root of n. We get this particular set of plots, and now we can see some of the other observations having bigger plotting points. For this particular data set, though, I have found that using a 1/4 root seems to work well. So when I use that here, now we can see some of these plotting points being larger than what they were before. We don't have such a big difference between number 3 and the rest. That can be useful then to identify that. Notice, for example, 15 and 10 here are bigger than, let's say, some of these other ones down there. Okay. Now, let's print off the actual numerical value so we can take a closer look at the corresponding observations. So inside of, let me actually come back here. Inside of save.info1, where I save from examine.logistic.reg, we see a list. And it's a list of everything that's being saved. And so what I can do is just print off those things that I'm interested in. So I create a data frame. I put my original data, w.n, in there. And this -4 basically says don't use the 4th column. You can look back at w.n to see why we don't want the 4th column. It's not a big deal. I put in pi.hat. I put in the standardized Pearson residuals. I also put in, remember, those tail probabilities that we looked at before as a measure of how extreme a particular standardized Pearson residual is. I have the delta x squares. I have the Cook's distances. So if I go ahead and do that, all these values print to my screen. Let me actually come back over here and take a look at it this way. Now, if you have a lot of observations, you wouldn't necessarily want to do this. You would somehow want to limit those values that are being printed to just maybe those that have, let's say, a large delta x squared, for example. If you're unsure exactly how to do that, let me know, and I can give you some help if you're in my class. But let's once again take a look at some stuff, and a lot of this will be similar to what we've seen before. So when I had a distance of 18 yards, 2 successes out of 3 trials, my pi hat's 0.98, the standardized Pearson residual is negative 3.58, but we know that that's using a standard normal approximation is not going to work well here. Here's that tail probability that we've seen before, 0.07. If I were to square negative 3.58, I get the 12.78. And look at, here's my Cook's distance, 0.02. Observation 3, this is the one that was really highlighted on those plots. The 20-yard place kick, 776 successes out of 789 trials. There's that large standardized Pearson residual. Here's the square of it, and look at Cook's distance here. Happens to be also 13.16. This is that very large one that was away from everything else. So what this is saying is that this particular observation is influential, or could be influential. And in the end, this actually does make sense for why this would occur, because we have 789 place kicks for that one particular observation. You know, if this is about half the data set, of course, that's going to be influential. But still, as we go along and look at this data set further, we're going to find ways that we can handle this issue here. And in the end, if we simply add a PAT variable to the data set, then we no longer have this issue there. Okay. So you can take a look at some of these other values on your own. Let me actually take a look at one more here. Number 34 is kind of borderline from what we see. Let's take a look at it. So here's 34. We had 16, let's see here. Oops, I was actually looking at the wrong one, excuse me. Here's 34. 11 successes out of 15 trials. So I had an estimated probability of success of 0.49 from my model. The standardized Pearson residual was 2. Notice the Cook's distance value of 0.17. That tail probability is 0.05. You know, if we can trust a standard normal approximation here, and we do have, it's not going to be perfect, but we do have essentially 16 possible values that W could take on here. So it's going to work much better than when we had only 3. Then we would have to say, okay, is 5% of the time getting something like this unusual? Well, you know, it goes back to when we were talking about before. If I had 100 observations, if the standard normal distribution approximation works, I would expect about 5 out of 100 to be outside of plus or minus 2. I think this is actually what we're seeing here. Well, I don't have 100 observations. I have about 50. And so we would expect about 3 to fall outside that plus or minus 2 range when the standard normal approximation works. And so I'm not necessarily really concerned about this particular observation as being fit poorly. But I think it's also good to look back to something that we did back in chapter 2 to compare this, what I call like an ad hoc way of assessing a model's fit, where we use the estimated probability on the y-axis, the distance in the place kick on the x-axis, the size of the plotting point corresponds to the number of trials per distance. And so here's that number 3 that we saw previously for the that basically represents a large number of PATs. Here's that number 1. And we said at the time, well, if I had a small plotting point here, this is maybe not something that we have to worry about, because it just so happened 1 out of 3 times we did not have a success. We can see some other ones. Notice how 34 kind of sticks out. It's a larger plotting point because we had 15 observations, and we can see that there is some distance there from the model. And that's what essentially that some of those diagnostic measures are picking up on. Okay. So this section then concludes talking about how we can use these goodness of fit statistics and how we can use these influence measures. And as what we've seen in the past in this model assessment, these measures are not perfect. What they represent is a way for you to think about if you have something outside the boundary lines that you might want to go further, investigate it further, see if you can explain why something's occurring in terms of, let's say, a large value. We've talked about also how perhaps one could use subject matter experience to understand why something's happening like this. In a future example, when we take a look at the place kicking data again, basically from the start of the model, start of the process of finding particular variables to the end of the process of assessing the model's fit and concluding on one potential model, you're going to see some very good stuff in that example that will help guide you in other data sets about how to approach problems that may pop up with a particular model, when to be alarmed and when maybe not to be alarmed, and also suggestions about how to handle the potential problems. So more on that later. That concludes in this section.